Okay, thank you very much. First of all, I am very happy to be the part of IGF 28, Trial Conference on Fracture and Structural Integrity. Uh, my name is Negewo Getu Bogale, PhD student from Department of Transport, Rudan University, Russia. The title of my article is Simulation-Based Optimization of Molten Pool Position in Sand Casting of Complex Steering Knuckle Geometry. These articles are this article is prepared in three sections. The first section is introduction parts. Second section is analysis, and the third section is uh, results of the analysis. Introductions. Casting remains one of the most significant and prevalent manufacturing techniques across numerous industries. Sand casting is the oldest techniques instead of today's emergence of scientific advancements and innovations like 3D printing. This traditional method is favored by the artisans for the following reasons: low tooling costs, suitability for low volume production and prototypes, high versatility in producing complex parts, relatively fast and ease of modification compared to other methods. Parts of automotives, which are produced by casting process, are engine blocks, cylinder heads, pistons, crankshafts, camshafts, intake and exhaust manifolds, transmission housings, gear, gearbox castings, torque converter housings, control arms, knuckle and hubs, steering knuckles, brake calipers, brake drums and rotors, structure and chassis components, subframes, cross members, and the wheel hubs are uh, manufactured or produced through casting process today. The objective of this article is to find the proper molten pool position in sand casting of complex steering knuckle geometry through simulation. To understand the parts which we are going to simulate is steering knuckle. In the context of automotive suspension, steering knuckle is a specific part that encompasses the wheel hub or spindle and establish a connection with the suspension and the steering components. The knuckle, also referred as the spindle, serves as the suspension element where the wheel bearing is housed, acting as the link between the wheel and the suspension system. Here, the application area of steering knuckle in automotive, two-dimensional illustration and a 3D illustration of steering knuckle is listed here. Methodology. The casting simulation employed the same material, which means the material selected for simulation is the same to identify any potential casting defects. For the analysis, 3 gates from different sides of components were selected, and 3 of them are utilized to investigate the defects. The material selected for steering knuckle model is the cast iron GJS 7002, characterized by a melting point of 1543.15 Kelvin, while the mold utilized is green sand. Alter Inspire casting simulation software is utilized for identification of parameters purpose. Simulation. To understand casting simulation, it offers numerous advantages, such as ability to forecast turbulence or laminar flow of molten metal liquid during the casting process, detect potential inclusions, and predict solidification behavior and timing. Casting defects play a crucial role in determining the quality and the reliability of casting components. Porosity, shrinkage, and misruns are common issues that can compromise the structural integrity and the functionality of the final product. Casting simulation software provides a comprehensive solution to manufacturing challenges by creating a digital model of the casting process. Casting simulation software plays a crucial role in the manufacturing industries, not only to identify problems but also preventing them. It accurately predicts the flow of molten metal, solidification patterns, and the final product's formation. And the figures, green arrow shows the position of pouring the molten metal. The simulation analysis which are examined in these articles are maximum stress, maximum temperature, mold erosion, last area, cold shear, and solid fraction. Here, the simulation analysis of maximum stress. The green arrow, as listed first, shows the direction of uh, pouring molten metal into the mold. Here, the maximum stress which occur during casting in the first phase or in the first analysis is 1324.96 megapascal. On the second, 9869.91 megapascal. On the third, we have 1497.4 megapascal. Analysis of maximum stress uses us to understand or to know the concept from mechanics which our material which is selected for steering nickel can withstand. So we will choose maximum stress which our part or the material selected for our parts can withstand. The second simulation is maximum temperature. The maximum temperature in first analysis is 1270 degrees Celsius, 1164.41 degrees Celsius, and 1165.02 degrees Celsius on the third analysis. This maximum temperature analysis can use us to get the homogeneous solidification in our parts. Simulation analysis of mold erosion. If the mold erosion are uh, analyzed in three molten position parts, in which parts can occur the maximum or the defects which may occur by mold erosion. This is a mold or erosion which are caused by uh, when we are pouring the molten metal into the mold. Here, 1.84 meter per second on the first analysis. On the second analysis, the maximum mold erosion which may form it in the second analysis is 2.03 meter per second. And on the surfaces, mold erosion is 1.23 meter per second. The next simulation analysis is last air. This is the main defect on every casting. This is the air which is trapped in the mold during casting or pouring molten metal into the mold. Here, the red sections are the air which is trapped in the parts during casting process. Here on the third section, the last air are just shown by red color. On the next analysis of cold shed, the cold shed is 105.1 on the second analysis, 106.95 on the second, and 0 in the third analysis. The next analysis is solid fraction. This is the defects which may occur during demolding after or on the solidification. Here, solidification fraction 0.1 on the first phase, 0.6 on the second, and solid fraction is 1 on the third analysis. Result and the discussion from this analysis. Depending on the results of simulation, analysis 3 is the best for steering knuckle casting with zero cold shed optimization. To optimize last air, it is necessary to make overflow hole during casting, as shown in the figure below. Here, the best pouring position is as shown on this feed or analysis 3, and the last air can be optimized by making overflow as shown on the figure. Discussions. Pattern can be prepared from wood or metal. Improper solidification process of metal may result in shrinkage, segregation, and various other defects. Use air cooling only. Rapid cooling in specific regions, along with more gradual cooling process in others, may lead to warping, cracking, and the development of internal stress. Misaligned cores may result in thin areas or cause cracking. Impurity. Unwanted materials found in molten metal may lead to the formation of inclusions and porosity. When filling the mold, it is important to pour at a slow peak to reduce the introduction of air bubbles into the mixture. Additionally, employing the vacuum degassing method can effectively eliminate any trapped air bubbles. Uncontrolled and rough pouring can lead to the entrapment of air bubbles within the castings. Casting defects can occur when molten metal is either too hot or too cold. Adequate ventilation can lead to gas entrapment in the development of blowholes. The key findings of this research are the metal or the material selected for casting is cast iron, sand, green sand, the mixture of silica and chromite sand, bentonite or clay 5 to 11%, water 2 to 4%, inert sludge 3 to 5%, anthracite 0 to 1%. Minimum temperature of molten metal 1165.02 degrees Celsius. Maximum stress which occur in the mold is 480.4 megapascal. Last air optimized by overflow hole as shown. Pouring molten metal velocity is 1.29 meter per second. Maximum pressure is 12,811.06 Pascal. Mold temperature 1,543.15 Kelvin. Solidification time is 309.20 seconds. Filling time is 2.884 seconds. Total shrinkage volume is 0 meter cube. Conclusion. This study involved casting simulation of steering knuckle to enhance the quality of casting, to examine the optimal positioning of the molten pool. To achieve this, three distinct angles were selected and analyzed. Within the third angle, ultimately chosen for the manufacturing process as shown below. Acknowledgements, thanks for my advisor, Professor Kazem Reza Kashyzadeh, for his great help. Thank you very much.